Hello students, in the previous lecture we have defined left coset and right coset and also proved some properties of left as well as right cosets. Now in this lecture we'll prove some the remaining properties of left and right cosets. The three properties we have just proved in the previous lecture, and now fourth property is if H is a subgroup of G, then the group G is equal to the union of all the left cosets of H in G, and second part is G is the union of all the right coset of H in G. Now we'll prove one part first, and second part we'll prove you prove yourself in a similar way. Let H be given H is a subgroup of group G, and let E, A, B, C, and so on to infinity be all the elements of a group G. Therefore, H into E is equal to H, HA, HB, HC, and so on to infinity are all the right cosets of a G. Now, what to prove? Our aim is to prove that G is the union of all the right cosets of H in G. So, in order to prove this, we have to prove that G is a subset of H union HA union HB union HC and so on to infinity, and second part is H is a H union HA union HB union HC is a subset of G. Subset of G. If we'll prove the part for the proof of this, let X belongs to G be any element of G. G. Therefore, Hx is right coset of H in G. Hx is X belongs to G and Hx is the right coset of H in G. Since H is a subgroup of a group G, therefore E also belongs to H. Therefore, E belongs to H implies E belongs to G. Identity element of the group and subgroup is same. Therefore, E into X belongs to E belongs to H, E into X belongs to Hx, right coset. That is E into X is equal to X, X belongs to Hx. So this implies if X be any element, means any arbitrary element, if we change X is equal to E, X is equal to E, E into E belongs to E into E belongs to H. So if X is equal to A into X is equal to A into H, and so on. This implies because X is an arbitrary any element of H, so this is true. This is true for all X belonging to G. Implies X belongs to H union HA union HB union HC and so on to infinity. This is the first part. Now let us do the second part, that is H union HA union HB union HC union so on to infinity is subset of HG. This is subset of G. Sorry. Let HA be any right coset of H in G where it belongs to G. Let HA be any right coset of H in G where it belongs to G. HA. So let X belongs to HA. If X belongs to HA, then X will be type H into A, H for some H belongs to H. For some H belongs to H. Since H belongs to H, therefore H belongs to G. And also A belongs to G. Therefore H into A also belongs to G. Because H is a subgroup of G. If H, since H belongs to H, since H belongs to H, for some. Therefore H belongs to G. H belongs to G and A belongs to G, G a group, therefore H goes equal to H into A belongs to G. That is, what is X? X is equal to HA. This implies if X belongs to H, X belongs to G. Now, first, X belongs to HA, we have shown X belongs to H, X belongs to H, X belongs to HA, and we show x belongs to G. Now, if we take this x to be any arbitrary element, if we take different values of h from here, so we'll get different x. So this first and second implies for h equal to e, h equal to a, h is equal to b, and h is c, so on and so forth. If x is equal to a, h is equal to a, h is equal to b, h is equal to c, and so on and so forth. This x equals to h, h a, x equals to c implies, or implies their union. If h belongs to G, for all A belongs to H, for all H belongs to H, therefore union of A belongs to G, union of all A belongs to G of HA is the subset of G. That is H union HA union H union C. Complete is subset of G. Means if what we have proved here in this theorem is this property, if H is a proof G, then G is the union of all the right cosets of G. Similarly, you can prove for the left cosets of G. Similarly, you can prove for the left coset of the G is a union of left coset of H in G. Now, next property is if H is a subgroup of the G, then there exists one correspondence between any two. Between any two. Number one, right coset such in G. Second is left coset of G. One correspondence between any two right coset of G and any two left coset of G. So proof is given H is subgroup of G. Let H A and H B are two right cosets of H in G, where A and B come G. Now define a function f from H A to H B by f of H A is equal to H B, f of H A to H B for all H A belongs to F H. To prove, what to prove? One correspondence means f is, our aim is to, in order to show that the two right cosets have a one correspondence means we have to show that f the mapping defined from one right coset to other right coset is 1 1, and this mapping is on 2. It will prove this f is 1 1 on 2 implies the two right cosets of H in G have 1 1 correspondence. So to prove the f is 1 1, let x belongs to H A. Then H A, if x belongs to H A, such that f of x is by f of y. Now we will show that x is equal to, since x and y belongs to HA, so what type of x and y will be? X will be of type H1A and y will be H2B. H1A and H2B for some H1 H2 H. Therefore, f of x is equal to f of y. Substitute x and y. F of H1x is equal to f of H2B. And their image definition of the mapping, the image will be, if they are equal, their image will be equal. Then H1B is equal to H2B. Cancellation law holds true in a group. Therefore, applying right cancellation with B inverse, so implies H1 is equal to H2. Apply the right cancellation by A. This implies H1A is equal to H1B, implies X is equal to Y. Like mapping F from one coset to right coset to other coset is 1 1. Now to prove F is onto function f of x equal to y is onto if for each y belongs to Rf, name the function, we have a unique x belongs to f. Let's take y belongs to hb. If y belongs to hb, y will be the type hb. So h will be for some h belongs to h. Now we want to find this pre-image. So let us take x belongs x is equal to ah. Let's take x belongs to h. Since h belongs to h, so ha belongs to ha. Take x equal to ha. Since h belongs to h, so ha belongs to capital H. Implies x belongs to ha, where x is equal to h belongs to h. Therefore, f of x is equal to f of x is equal to f of ah is equal to f of hb. is equal to y. Implies f of x is equal to f of h is equal to f of ha is equal to f of hb is equal to y. Implies f is on 2. F is buffering from one right coset to other side, which is 1 1 on 2. Implies ha and hb have 1 1 correspondence. Now the sixth property, if h is subgroup G, then there is 1 1 correspondence between the set of left cosets of H in G and right cosets of H in G. Then left set of left cosets H in G and right cosets in G. So that's given H is subgroup of G. Let L and M be respectively the set of left cosets and right cosets of H in G. Therefore, L will be equal to left coset H such that A belongs to G, and M is equal to HA such that A belongs to G. Now let's define mapping from F from L to L. By F of EH capital H is equal to H of A plus for all events to G. If A belongs to G, then inverse also belongs to G, and hence H inverse also belongs to M. Therefore, F is a mapping from L to L. We will define this mapping. Now our aim is to show that the result is proof complete. We have to show we have proved F is well defined, F is 1 1, F is all. So first part is, let us define F is a well defined mapping. Let A be belongs to G such that HA is equal to G, such that H is equal to H. So then using second property, if H equal to HB, this implies this is true if and only if A inverse B is equal to belongs to H. Second property. Now this is true if H inverse B, H inverse A B belongs to H, implies if and only if this is true, this is first property. Implies if and only if H of A inverse B belongs to H. And this is the H is a subgroup of G, right cancel hold in H. So applying right cancellation law to this. This is true if and only if H in A inverse B inverse is equal to H B inverse. Now a scheduler holds true. H inverse B inverse is equal to E to H inverse. So H inverse E is equal to A inverse is equal to H inverse. This implies what is this? This is the image of F of AH and this is the image of F of BH. Implies the definition function implies F is a well defined function. Now B part will be with the reverse of the above. If we proceed in reverse order, we will prove that F is 1. If we start from here, F of H is equal to FB and we'll reach here. H is equal to BH implies F is 1 1. Now C part is F is on. Let HA belongs to M be arbitrary and any element. Because it belongs to G implies G group, the inverse also belongs to G. So A inverse H belongs to L. A inverse H belongs to A inverse H belongs to L. Right? So A inverse H belongs to L such that F of A inverse H is equal to H of A inverse of A equal to HA. So F of inverse is equal to HA implies F is on to A, B, C, A, B, and C implies the mapping F from L to M have 1 1 correspondence and the set of left coset of H in G and the set of right coset of H in G have 1 1 correspondence. Next part is if H is a subgroup of a group G, H is a subgroup of group G, then HA inverse is equal to inverse H where inverse. Proof is given H is equal to, to prove it, H inverse is equal to A inverse H. Two parts, H inverse subset of A inverse H and A inverse H is subset of H inverse. First part is to prove first part, H inverse is subset of A inverse H. Let us take X belongs to H inverse. That is X is Y inverse, and for some Y belongs to HA. If Y belongs to HA, Y will be of the type Y is equal to HA for some H. So X will be equal to substitute only Y here. X is equal to H inverse is equal to A inverse H inverse. Since H belongs to H and H subgroup, therefore H inverse also belongs to H. Belongs to H. Therefore, A inverse H inverse, H inverse belongs to A inverse H. What is A inverse H inverse? A inverse H inverse is equal to X. The X inverse belongs to inverse H. So this implies X belongs to A H inverse. We have shown that X belongs to A inverse H. Implies H inverse is equal to subset of A inverse H. Second part is we will prove that A inverse H is a subset of H inverse. Let's take X belongs to A inverse H. So what kind of this X will be? X will be A inverse H for some H inverse H. And suppose G H inverse H, H inverse of H equal to H. So replace this H by H inverse of inverse. So that we know. So now A inverse H inverse inverse is equal to can be written as H inverse A whole inverse. X belongs to A inverse H, and this is equal to this. We have shown that X is equal to H inverse A inverse. Since H belongs to H subgroup, H inverse also belongs to H. So H inverse A belongs to HA, and H inverse A inverse belongs to HA inverse. This implies X belongs to A inverse H, and we have shown that X belongs to X belongs to HA inverse. So this implies H inverse A is subset of HA inverse, and the P and P implies result. Thank you.